Guys, so we're going to continue chapter 23, and last time actually we had an example on how to find the electrostatic force between any two charges, Coulomb force between any two charges, magnitude and direction. So we'll start this lecture today by having an example on what we have studied so far. So assume that we have two charges, Q1 and Q2, as you see on the figure. Q1 is equal to, has a charge of 2 microcoulombs. Micro is 10 to the power minus 6. So 2 times 10 to the power minus 6 coulombs. And charge number 2 has a positive 3 microcoulombs. Q1 is located at R equal to 2 centimeter and 1 centimeter. That means that X, it's at a coordinate, at a position of X equal to 2 centimeter and Y equal to 1 centimeter, while Q2 is at 4 centimeter and 3 centimeter. We need to find the force F12, the magnitude of the force of Q1 on Q2. Magnitude. We need to find the magnitude only. Any idea? Any idea how to solve this? We need to find only the magnitude of the Coulomb force. Excuse me? We did not talk. This is your first time to attend? We did not talk anything about electric field yet. So we know nothing about electric field. Yeah, but still, we know nothing about the electric field yet. We need to find the electrostatic force, the force between two charges. One of them is 2 microcoulombs. The other one is 3 microcoulombs. And the distance between them is not given, but the position of the two charges are given. Any ideas? Yes?
We get, first of all, we get the R, the distance between them, and we put the values in the formula KA, Q1 multiplied by Q2 over R.
Okay. I forget your name. Tariq is saying, Tariq is saying actually, that's not that hard. The force F12, according to Coulombs, it says it's equal to K, and that's a constant, times Q1, Q2, divided by the distance between them squared. And since we were talking about only the magnitude, then this is the formula to find the magnitude of the force. Tariq also saying that we know K, that's constant. We know Q1, that's a given, it's 2 microcoulombs. We know also Q2, that's a given, that's 3 microcoulombs. But the distance R1 to the distance between the two charges is not given, but we can get it because we know the position of the two charges. So since we know the position of the two charges, we need to find, according to R12, any idea how can we find R12, which is square root of
2 squared and 2 squared.
x2 minus x1 all squared, right?
And y2 minus
plus y2 minus y1 all squared. And this we can get actually the distance between the two charges. That's easy. So if we know the distance, we plug it in here, we can find the forces between the two charges. x2 equals to
4.
It's 4. Actually 0.04. Not 4.
Yeah.
Am I right?
Yes.
Why is it 0.04 not 4? Because we have to go into we have to use the units of, do you know which system should we, which is, we use meter, kilogram and second. Meter, kilogram, second. So we have everything has to be in meter. So x2 is going to equal to 0.04 meter. x1 is equal to 0.02 meter, and y2 equals to, guys, 0.03 meters, and y1 equal to 0.01 meter. So now we know all what we need to calculate the magnitude of the forces between the two charges. So if we continue doing this, plug in the numbers, we'll find that R is going to equal to 2.828 centimeter. We have to convert that into meter. and the force between the two charges is equal to 67.5 newtons. Just plug in the numbers. Someone will ask me what's K? It's Coulomb constant. Should we memorize Coulomb's constant? No, guys, no. Do not memorize any constant. Do not memorize even the formula. Again, I'm going to keep repeating this till you stop memorizing anything. Okay, guys? So that's how we find the magnitude of the force. That's really easy. Just plug in the numbers. Direction. Can we find the direction of that force?
Yes.
What is the direction of that force? We need the force of Q1 on Q2. So what is the direction of Q1 on Q2?
Q2, Q1.
It's going to be along that direction. Along that direction. But we have to actually convert that into our Cartesian coordinate system, so we have to write it in IJ format.
Isn't it the other direction? Because Q2 has the greater charge.
Is it? So Q2 has the greater charge.
Yes, so it actually pushes Q1 away. Like towards Q1, the direction.
Did you ever skate?
Skate, yeah, but I failed miserably.
Okay. When you skate and you go and you push your colleague, and even if your colleague was Ala Waliyuddin, are you in class?
Is this class?
Yes. Then what happens if there is no friction? If you push someone when there is no friction, what happens? Both of you move. So when you push him, he pushes you back, and that's Newton's third law.
But I'm talking about the resultant force.
Yeah, a resultant force on a specific object.
Yeah.
We're talking about the resultant force on an object. Which one are we talking about? We're talking about Q2. We're talking about Q2, right?
Yeah.
The force on Q2. And the force on Q2 is going to be along that direction because actually they are pushing each other away from each other.
Yeah.
Okay?
But one is pushing more than the other, right?
No. Are they? Are they? Then if we do that, then we're going to violate Newton's third law.
But what about the charges? One is more than the other. It doesn't have any
But
relationship?
look at the force. Look at the formula again. The force F12, the force from Q1 on Q2 equal to K, Q1, Q2 divided by the distance between them. How about the force from Q2 on Q1? The same. The magnitude is the same, but the direction is different. It's in the opposite direction. And this is exactly Newton's third law. Okay? So all what we have to know to do to find the direction of the force is to find that angle theta. You see that angle theta. If we can find that angle theta, then we can simply find the direction of that force. So that theta, and the force along the x-axis is going to be F12 cosine theta. The force along the x-axis is going to be F12 cosine theta, and the force along the y-axis is going to be F12 sine theta, and this is going to be the force along the y-axis. So it will have that vector, it's a vector, force is a vector, will have two components, one along the x-axis, and that's going to be the magnitude of the vector times cosine theta, and another component along the y-axis, and this is going to be the magnitude of the force times sine theta. So all what we have to do is to find cosine theta, and simply that's x2 minus x1, cosine theta, that's this in here, divided by r, which is x2 minus x1 divided by r. We know r, we just calculated r a minute ago. Then we know what's x2 and x1, then we can simply find cosine theta and sine theta and plug in the numbers again. We'll find the two components of the forces, and the two components is going to be 47.74 Newton, and that's the force along the x-axis, and the force along the y-axis is going to be 47.74 Newton as well. let me finish this, and I'll take your question in a minute. But let's go back and look at the magnitude of the force. It was 67.5 Newton, while the x component is 47 and the y component 47. How come the two components are not adding up to the 67 Newton? Because that's a vector quantity. And the magnitude of the force, if you know the component, if you know Fx and Fy, you remember the force should be written as Fx, that's along I, plus Fy, that's along J. Correct, guys? Right? So the magnitude of that force, as we know from Physics 111, from vectors, chapter 3 in Physics 111, will equal to Fx squared plus Fy squared under the square root of Fx squared plus Fy squared. And if we do that for the 47.7 and the 47.7, you will exactly get 67.5 newtons. Sharif?
How come this is like 47.7 newton is a lot of force? It's a big quantity.
Electric force is a lot of force. The electrostatic force, that's huge force. And we'll talk about it in a few minutes. We'll talk how important is that force. How significant is that force. So far we're talking about two charges. Only two charges. And you know, life is not that easy. You'll never have only two charges in a real life situation. You will have more than two charges. So assume that Amr has a positive charge. Amr has a positive charge. And all of you guys, all of you also have a positive charges. It doesn't matter if the same amount of charges or not, but now we need to find the forces from you on Amr. I'm not talking about direction for now. I need to find the forces from all of you on Amr. What to do? Amr, raise your hand. So what to do?
Calculate each force and how it's acting.
Sharif is saying, well, I'll take it easy. What I'm going to do is I'm going to calculate the effect of each charge on Amr. So the force from Sharif on Amr is going to be along that direction. Along that direction. And if we know that the amount of the two charges and the distance between them, we can easily find the magnitude and the direction of that force. Then, what's your name? Assam. Then Assam will find the force also from Assam on Amr, magnitude and direction. Then add the two forces together as vectors. And we know how to do this. Then add them as vectors. So let's assume that the force from Sharif on Amr is going to be F12, Amr, that's charge number 2, will equal to 3I plus 5J. Of course, and the unit is Newton. So it's 3 newtons along the x-axis and 5 newtons along the y-axis. That's the force from Sharif on Amr. And the force from Assam on Amr is going to be 2I plus 7J. Newton. What is the resultant force? What is the total force on Amr? It's going to be 5I plus 12J. And if we keep doing this for the rest of the charges, then we'll find the total force on Amr. We'll find the total force on Amr. And we add those as vectors. Okay, guys? Okay, guys?
Is there an easier way?
This is the only way.
But yeah.
And we call that the superposition principle. We call that the superposition principle. If the charges are separated, like you see, you are a charge, but there is no charge between you and your colleague, and so on. But if we have a continuous distribution of the charges, then it gets a little bit harder because we have to do an integration. Then I'm not going to get into that now. Okay, guys? So if we have separated charges, like you right now in class, I'm assuming that you are charges, and we need to find the effect, the forces from all of you as charges on me as a charge, then simply it's the force between charge number 1 on me plus the force from charge number 2 on me, force from charge number 3 on me, and so on. Then we add them as vectors. Of course, if you have an infinite number of charges, then it gets complicated, but it doesn't get. If we have infinite number of charges, then we go to what we call it a continuous distribution of charges. Then we'll do integration. It's not that hard. It's easy, but it needs a little bit of mathematical tools with us, and I'll teach you how to do that. Yes.
So can we finally get the torque result of the magnitude and the direction?
Of course. So now, this is the total force. Now it's given in the vectoral form. What is the magnitude of that force? What is the direction of that force? What do I mean by direction of that force? What do I mean by direction of that force? What do you mean by theta? Angle from what? Angle between the vector and the x-axis. Measured from the positive x-axis counterclockwise. So this is the vector total. That's the force total. That's the angle theta. We measure it from the positive x-axis to the vector counterclockwise. This is the definition that we have agreed upon in Physics 111. How to find the direction of any vector. Yes?
We calculated F12 and F32, but there is no force between 2 and 3.
But now you're measuring the force on either charge number 3 or charge number 1. We're talking about the forces on charge number 2.
You mean the force between 1 and 3 doesn't affect the
No,
forces?
no. We're talking about the force on 2. Keep in mind that we're talking about the force on 2, not that. What is the total force on the whole system?
0.
Thank you. Why is it 0? That's Newton till below. The force between me and Sharif, if Sharif is pushing me in that way, I'm going to push him in the opposite direction. 2 equal forces, opposite direction. The net force on the whole system, Sharif and I, is 0.
And this is equal to if we have 2 charges?
Yeah. I'll just give you an example of Sharif and I. That's 2 charges. Doesn't matter if it's positive or negative, but the force from Sharif on me, magnitude of the force from Sharif on me, is equal to the magnitude of the force from me on Sharif. Right? But in opposite direction. So if you add those as vectors, you get 0. So the system has a 0 force on it. And if the system does not have a 0 force on it, what happens? It moves. The whole system moves. The center of mass of the system moves. If you remember what we have studied in Physics 111.
Could you give us an example of that? Where the system moves?
Yeah, the whole class will move. All of us will move if the net force on us is not 0.
No, I mean with electrostatic forces of attraction.
Oh, no. Okay, but not now. Okay, guys, so that's the principle. That's the superposition principle. If you have more than one force, find the force on the specific charge from another one, then add them and add all those forces together. You get the net force on that charge. So, saying that, I'm going to give you a minute to read this act and try to answer the following statements. Tell me if they are true or not. I give you a minute just to read it first, then I'll give you the statements after. Okay, simply we have two charges, Q1 and Q2. Q1 has a charge of positive Q, and Q2 has a charge of positive 2Q, so double the amount of the charge on Q1. You insert a charge Q3 somewhere between them, at a distance r from Q1 and at a distance 2r from Q2. Which of the following statements is correct? The force on Q3 can be 0 if Q3 is positive. The force on Q3 can be 0 if Q3 is negative. The force on Q3 can never be 0. The force on Q3 can never be 0 no matter what the non-zero charge Q3. No matter what is the value of Q3. What happens if Q3 is positive?
It will be in the same. It will be in the same place.
What will make Q3 move? If we have a net force on it. This is the answer. Do we have a net force on Q3? Do we have a net force on Q3?
Yes.
Well, the total force on Q3 is going to be, force from Q1, so it's a force from Q1 on Q3 as vector plus force from Q2 on Q3 as vector. So what is the force from Q1 on Q3? It's Q3 divided by R squared. Okay. In what direction? I. Why is it I?
In the positive direction.
Well, Abdullah is saying, well, I'm going to choose this to be my positive x-axis, and this is my negative x-axis. So the charge from Q1 and Q3, since if I assume that the Q3 is positive, it's going to be a repulsive force. So Q1 is going to push Q3 in that direction. So the force from Q1 on Q3 is going to be along the positive x-axis. That's why he said I. Good. So we got that. Plus, what is the force from Q2 on Q3? Right? That's Q2 times Q3 divided by 2R all squared, that's 4R squared. 2R all squared, that's 4R squared. And in what direction? Can we get 0?
No.
Simply? So this, guys, is going to be half of that. That was 4, and we had 2 in here. Okay? Okay, guys, so this is not correct. Statement number 1 is not correct. How about statement number 2? What happens if we reverse the charge on Q3? So instead of having a positive charge, we get a negative charge. The direction is going to be opposite. But the magnitude is going to be the same. It's not going to change. So statement number 2 is also not correct. It's not true. So no matter what is the sign of Q3, you will not get a zero force on Q3. So that's C, as you said. Okay, and that's the answer, and that's the explanation. I will leave that for you to read it when you study. Another one. Can you solve that one? Guys, can you practice and can you solve that one? You have 3 minutes to finish that one. 3 minutes. Feel free to ask me anything you want. Solve.
دكتور هو في القانون ده في R squared صح؟
What's R squared? Yeah. Let me write the Coulomb's law for you guys on the board. Coulomb's states that force, electrostatic force equal to K, Q1, Q2 divided by the distance squared. K times Q1, Q2 divided by R1, 2 squared.
The value of K?
It's 9 times 10 to the power 9 times 10 to the power 9 Newton meter squared Coulomb squared. But I didn't really need you to get the final answer. I just want to see if you can get this vector form at least in a correct way. The vectorial form for the force. We need the force on Q2.
On Q0.
Oh, sorry, I'm on Q0. On Q0. What is the direction of the force from Q1 on Q0?
J.
J, positive Y. Are you sure?
From Q1 to Q naught.
Mm-hmm. Oh, negative J, thank you. Why is it negative J? Because it's an attractive force. Because you forgot to look at the sign of the two charges. Common mistake.
Because doctor, I substituted the value, its value by -1.
Yeah, but you find the direction by the physics. You look at the sign of the two charges, and you find out if it is an attractive force or a repulsive force. Ala, are you done? Can I see the solution? Okay, please do it. No, your nose is not enough. I want to see the solution. Yes. Q0, it's a negative 1 microcoulomb. So Q0 is a negative charge. Q1 is a positive charge. Oh, okay. Because it's okay. Q0, that's a negative charge. Q1 is a positive charge. So what will be the direction of the force from Q1 on Q0? What kind of force are we going to have? We're going to have. It's an attractive force. So Q1 is going to pull Q0 in that direction. Right? So if the Q0 is free to move, that's what's going to happen to it. And the objects move in the direction of the net force. How come? If I pull you, can you move in the opposite direction? Oh, but we're talking about the force on Q0, not on Q1. Again, We're talking about the force on Q0, not the force on Q1. If we're talking about the force on Q1, then you're right. Q1 is going to move along that direction. If it's free to move, it's going to move along that direction. So it's going to be attracted to Q0. So the force on Q1 is going to be along the positive Y. Yes.
I can't describe the vector acting.
You need the angle theta. You need the angle theta. Yes, go ahead. Go ahead. It's not going to move. Both of them are fixed in space. They will not move. But I'm saying if they are free to move, in what direction will it move?
How's it going to move electrostatic force and Q1 is acting Q1, the same force Q1 is acting Q0. They have the same forces.
I'm saying, okay guys, what I'm saying is they will not move because they are fixed in space. But assume that somehow I'm attached to the wall, and I cannot move. But you're free to move because your chair has some wheels on it, so you're free to move. If I pull you, what's going to happen? You're going to move in that direction. Okay? Let's assume that both of us are on chairs with wheels like this. And if I pull you, what happens? We both move. Okay? But they are fixed in space, and the force on Q0 is going to be an attractive force, so it's going to be Q0 is going to be attracted to Q1. So this will be the direction of the force from Q1 on Q0. Yes, Abdullah. Okay. Ala, are you done? Can you see it?
Okay, طب انا ممكن اعمل resolution Q2 in terms of in X, Y when I added.
You do a resolution for a vector. So you mean the force from Q2 on Q0, not Q2, because you said if you do a resolution for Q2.
Okay, yeah.
Yeah. Okay.
Q2 on Q0.
Oh yes.
In time, adjacent opposite hypothesis.
Why do you have to get that?
Oh, because we need to you need to write down the force F20 in a vectorial form, so you can add it to F10. You need to apply that formula. I erased it. That one. You need to apply this, but on Q0. The net force on Q0 will equal to F10 plus F20. So you have to find F10 in its vectorial form, and you need to find F20 in its vectorial form. Right? Good. Excuse me. Can we do this together? Now, F10.
Okay, هتبقى
K. It's, I'm going to teach you a trick. So pay attention to this simple trick. It's very easy. It's going to make your life much, much easier from now on. What is the magnitude of Q? What is the absolute value of Q0? 1 microcoulomb, right? I did not put any sign in here. What is the magnitude? What is the absolute value of Q1? 3 times 10 to the power minus 6 divided by the distance between them square. I'm going to leave that for you guys. Right? This is the distance between 1 and 0 square. Okay? I'm going to leave that for you guys. I'm going to leave it for you. What is the direction of that force? So I totally ignore the sign of the two charges, and I got the direction of the force by the physics. By knowing that this force is going to be an attractive force, then I will be able to find out the direction of the force. Then totally forget the signs of the two charges. This is F10. Now let's do F20. Let's calculate that. Plus F20. Ask.
Y minus Z.
What will be the direction of the force from Q1 on Q0? Are you sure?
From Q1.
On Q0.
Yeah.
Why is it up?
Q1 to Q0.
Yes, why is it up? What is the sign of Q0? Is it a positive charge or is it a negative charge? Negative. And Q1. So what will be the force between them? Is it an attractive or a repulsive force? That's why it's a negative. Okay. Now, F20, guys. It's K times 1 times 10 to the power minus 6 times Q3, which is divided by the distance between them squared. I'm going to leave that for you as well. 0.2 squared times. What is that? What is this? This is the magnitude of the force. But if you look at the force between Q2 and Q1, it's going to be along that direction. Is it Q1, Q0? It's along that direction. Right? It's along that direction. Then it will have two components. If it's along that direction, it will have two components. Component along the negative x. Positive x, and a component along the negative y. The positive x, the component along the x-axis will take a cosine theta. Cosine that angle theta that you see. And it's I. No, it's not. I said I. Again, I'm not that tall. This is the direction. Ala, can you help me out? You're the tallest in class. I want you to point this in the direction of the force from Q0 on to Q2. Yes, correct. This is the direction. This is exactly the direction of the force. Right, guys? We have to break that into two components. A component along negative y, right? And a component, because this is going into that direction. So if you assume that this will have, this is the arrow. This is the tip of the arrow. I didn't do it that way. I did it that way. This is the tip of the arrow. This is the direction of the force. This is an attractive force. So what happens? Q2 is going to attract Q0 because Q2 is positive, right? And Q0 is negative. So the force between them is going to be an attractive force again. Attractive force means that Q2 is going to pull Q0 in that direction. So the force between them is going to be along. The force on Q0 from Q2 is going to be along that direction. Right? Oh no, the arrow is just an arrow. No. It's going to be along that direction. Right, guys? Then if this is the direction of the force, then we'll have two components. A component along this and a component along that direction. So this component is going to be x, positive x, and this component is going to be negative j. Correct? Right? Thank you. That's why I said it's I, cosine theta. You find theta. Let me finish it, then I will repeat it again. Cosine theta, I, times I. This is the x component of the force, plus k, again, 1 times 10 to the power minus 6, 4 times 10 to the power minus 6, divided by the distance 0.2 squared times sine theta along negative j. Now, we can add those three terms together. You'll find a number times I plus a number times j. This is the force on Q0. Of course. Yes. I'll say it again one more time. Okay, guys?
We totally ignore the sign when we're working.
Yeah. We totally ignore the signs and we find the direction by the physics. Okay, Sharif? Okay, what did I do? I said that now I have two charges acting on Q0. They might be pulling or pushing Q0 depending on the relative signs of the charges. So I'm going to take it charge by charge. I'm going to look at the effect of Q1 on Q0 since we need the force on Q0. So I'm going to take the force from Q1 on Q0. What is the direction of that force?
Q1 on Q0?
Yes. Look at the board. What is the direction of that force?
Negative J.
It's going to be along negative J. Why is it negative J? Because it's an attractive force. So Q1 is going to pull Q0 along that direction. So the force on Q0 is going to be from Q1 is going to be along that direction, negative J. What is the magnitude of that force? Simple. It's K, Q, the absolute value of the Q. Totally forget the sign of Q's now, divided by the distance between them squared. That's easy. How about the force from Q2 on Q0? The force on Q0 from Q2. Is it an attractive or is it a repulsive force? It's an attractive force. That means that Q0 is going to be pulled along that direction by Q2. So this is the direction of the force on Q2 on Q0 from Q2. And we have to break that into components, x and y. The x component will take a cosine that angle theta. And the y component will be the sine of that angle theta. If you break that into two components, x and y, you'll find the following.
دكتور عايز اقول حاجه البوزيتيف والنيجاتيف تشارج لما يبقى فيها اتراكتيف فورس بنعرف منين ايه اللي بيروح على يعني حسب الماجنتيود بتاع التشارج ولا على حسب البوزيتيف والنيجاتيف.
It depends on which charges are you trying to find the force on. You're talking about Q0, the force on Q0. The force on Q0 from Q1. What is the direction of that force? The force on Q0 from Q2, what is the direction of that force? Right, that direction. Then you break it out to I and J. Okay? This is how we think about it. The force on a specific charge. Okay?
So if there is any unlike charges, the one will be attracted.
Unlike charges, they will attract each other, and like charge, the similar charges will actually repel each other. Let me finish here, then I will get back to you. Yes. Yes. Why is that cosine theta?
I know it's y.
Okay.
It's supposed to be negative.
The magnitude of the force, which is Q divided by the distance between them squared times cosine theta. K. Because that's the vector. You're getting the component of the vector. Okay, component along the x-axis. Guys. What's your name again? When Sharif asks something, that means you should listen as well, because I know that if you start talking to each other, what's going to happen is one of you will ask the same question again. Sharif asked. So please listen. Sharif is saying. What were you saying?
Why don't you do the x component force cosine theta? Why do you do it?
That's what we do.
You did it in a cosine theta.
Yeah, we did it. The force, we need to find the x component of any vector markers. Any vectors, okay? That's Physics 111, chapter 3. So guys, pay attention. That's X, Sharif, that's Y. Okay? This vector F. Can you find the angle, if this is the angle theta, can you find the two components of that vector? Cosine theta plus sine theta. I'm sorry, I forgot to add I and J. Correct? Correct? Now let's assume this is the force. This is the vector. And this is again the angle theta. Can you write this in the vectorial form? It's going to be, again, the x component is going to be along that direction, right? And the y component is going to be along that direction. So this is going to be f cosine theta along negative I plus f sine theta along negative j. And that's what we did exactly. Oh, okay. Guys, come on. You have a brain to use it. I cannot give you every single case on class. Then, in that case, that's Q0, that's Q2. The direction of the force is going to be along that direction. This is F. Can we break that into components? That's Fx and that's Fy. Fx is going to be F times, this is theta. This is theta. F cosine theta. And this Fy is going to be F times sine theta. Right? And that's exactly what we did. The force F, this is F, that's KQQ divided by the distance between the two charges squared. Okay? Okay? So if we plug in the values, we should be able to find the forces on Q0. That's going to be 40 Newton, 40 point something Newton. Do you have time? Okay. Are you sure? What time should we finish? 10 minutes? Okay. What happens? What does really happen is if you have a charge, it creates around it what we call it an electric field. If you have a charge, it creates around it an electric field. It's exactly as if you put perfume. It creates around you a field of smell. You smell, if we come closer to you, the smell will get stronger and stronger. Same thing with the charge. If you have a charge, it creates around it an electric field. And if there is another charge get affected by that electric field, it might get attracted or repelled by that electric field. That's exactly what happens. So actually, we have a scalar field and a vector field. This is the map of the United States, and if you took Physics 111 with me, you have seen that map before, and that's the same slide exactly before. Scalar field means you have a distribution of a scalar quantity over space. So what you see now is the temperature distribution over the United States. Temperature is a scalar quantity. It does not have a direction, so it does not mean anything to put a direction for those numbers. And we call that a scalar field. It's just the distribution of a scalar quantity. But we can have also a vector field. If we're talking about the wind speed all over the United States, I'm sorry, guys. Did I make a mistake right now?
The wind speed, it said speed.
The speed is a scalar quantity. If I talk about wind velocity over the United States, then in Utah, for example, in Utah, it's not enough to say that the wind speed is 84 meter per second or kilometer per second, but it's very important to say also the direction of that wind. It's the wind velocity, it's 84, and the direction is blah blah blah. In here, the wind velocity is 73, and the direction is east. It's very important to find the magnitude and the direction for a vector quantity, and we call that a vector field. So if you have a charge, it will have around it field, a vectorial electrical field, and we call that electric field. And we know that it's going to be a vectorial field.
Okay, I have a question.
Sure.
Oh, does that mean in الدايركشن يعني مثلا if you have a charge مثلا لو positive في charge negative يبقى electric field هيبقى عامل كده؟
We'll see. We'll see. Good question. Sharif actually is ahead of us, and he's saying, well, so what will be the field from a positive charge, and what will be the field of a negative charge? So before I go and answer Sharif, I want to summarize what did we have studied so far. Nothing. Coulomb's law and the superposition principle. That's all what we have studied so far. Coulomb's law says that if you have two charges, then the forces between them might be an attractive force or a repulsive force depending on the type of the charge. And we should be able to find the magnitude and the direction of that force using Coulomb's law. Then the superposition principle, it says that if you have more than one charge, you find the effect. If you need to find the force on a specific charge, all what you have to do is to find the force from each charge on that specific charge, add all those forces together as a vector, you get the total force on that charge. And we call that the superposition principle. Then we talked about scalar field and vector field. A very interesting example in here, guys. Assume that your friend can push their arms apart with a force of 100 pounds. How much charge can they hold outstretched? How much charge they can put? I can do this, that force by 100 pounds. How much charge can I have in my hand, in each hand? It has to be a charge almost equal to that 100 pounds in each hand. Because if I do this, what happens? If they are similar charges, they will repel each other. So I can do this by 100 pounds. Or what I have to do is to put in each charge, in each hand, an amount of a charge equal to what? So I'm going to leave that example for you to solve it at home. Then we'll discuss it next time in class. But before we leave, should I stop, honey? Save. Before I leave, I want to answer actually Sharif's question about electric field. So I'm going to skip this we're gonna go over that again next time, but I wanna go actually to see what did Sharif ask before we leave. Sharif said, what will be the field, electric field from a positive charge and a negative charge? I assume that what you see there, those are two positive charges. I'm representing the electric field by two different ways. That's not important. But let's look at that diagram in here. This is the electric field from a positive charge. It's out of the charge. It's out of the charge. And if from a negative charge, it's going to be into the charge. Why? Why is it out of the charge? How come we came up to that conclusion? This was going to be the topic of the Thursday lecture. And how to calculate the electric field, and what is the effect of the electric field on other charges. This will be the topic of Thursday lecture. Thank you guys. The assignment is going to be postponed since I did not finish.